All right, so here is our lecture all about air pressure. Here's how you're going to do your notes. You're going to go into Canvas. You will find in your modules for today, you've got this assignment right here. Again, this is found in modules. You're going to open the following guided notes. It's going to take you to a screen that looks like this. We will open up with our Google Docs, and then make sure you make your own copy so that you can edit it, make a copy, and share it so that anyone with who has the link can view it so that I can view it when you turn it in. So you're going to fill out those notes as we do this lecture. Let's get started, shall we? So we're talking all about air pressure and wind. Significant air pressure is often what causes weather events, but along with the air masses moving in. So just like our air masses and our fronts gave us distinct ideas of what kind of weather was going to be coming our way, our air pressure and the wind will also help indicate any kind of weather events that are happening in our area. First, we're going to discuss air pressure. So this is the force exerted by the weight of the air above it. So at all times, you have air pressure pushing on you from all of that air in the different layers of the atmosphere that we talked about. We talked about it being generally 14.7 pounds per square inch, but that can vary depending on, or that's the amount consistently pushing from the atmosphere. But we do have pressure systems just in general that move about, and they are sometimes on the range of thousands of pounds per square inch, but we don't feel it. It doesn't crush us because the pressure is exerted in all directions, not just down. So instead of being a single down arrow on a force graph, it is spread out more like a star. So we don't feel the effects as strongly. We don't feel the full effect of the air pushing down on us. Here's how we measure air pressure. We can use a mercury barometer or an aneroid barometer. This right here is an example of a mercury barometer, so that pressure, here's how it works. So we've got our container that is full of mercury, and it's got a tube on the inside that has created a vacuum right here. Because of the vacuum, when atmospheric pressure pushes down on the mercury that is in the cup or the bowl, that mercury is displaced up into the tube. And so the more pressure that is exerting down right here, or the more atmospheric pressure we have, the higher pressure, the more mercury is going to be displaced into the tube. And that is how we measure. Sometimes we measure in inches of mercury, or we can convert it to pounds per square inch. Okay. Here is how we graphically tell or distinguish air pressure. They're called isobars. So this is not originally how the data would look. The data would look like a bunch of numbers taken from areas all around of air pressure right here. Scientists and meteorologists have created this graph to show general regions of air pressure based on the results taken from this. So these are similar to topographic lines on a map giving elevation, meaning that as you move from bar to bar, we're having changes in pressure. So from here, we go from 1,000 pounds per square inch to 1,004 pounds per square inch to 1,008 pounds per square inch to 1,012 pounds per square inch to 1,000 and so on and so on. And as we go this way, we're getting lower, so we can assume that this might be 96 pounds per square inch of pressure, which is low. The spaces between each isobar indicate a pressure change, so we have a pressure change from right here to the middle of this Great Lake right here, which I believe is Lake Erie or Superior. I am not exactly sure. Okay, actually, just kidding, that's Lake Michigan. Awesome. Okay, so those are isobars. Again, they connect, they're lines that are connected lines of equal pressure. That's how scientists indicate pressure changes in an area. And that's often something that you might see on your Weather Channel. Why does air pressure matter? We care, but before we can say that, why do places have different air pressure? So solar radiation creates air pressure differences, or the energy that we receive from the sun can create air pressure differences as well. The differences in air pressure cause a phenomenon called wind. So wind is actually not something that just happens. It's because of these differences in air pressure. We talk about gradients often in science. So moving from a high to a low. Wind does the same thing. So air molecules don't want to be under high pressure, so they will move to they're always trying to reach equilibrium. So they don't want to be under high pressure and they don't want to be under low pressure. So high pressure molecules will move and try to space themselves out to a more equilibrium. That doesn't always happen. And when they try to move, that's what actually causes the wind. So wind is when air flows from areas of high pressure to areas of low pressure. Again, that gradient. You can think like if you took a cup of water, say we call that high pressure because all the water molecules are pretty contained, they're not going anywhere, and then you take that cup of water and you dump it onto the table. Now the water molecules are spacing out, they're spreading everywhere, it's dripping all over. That's because they want to move to the most comfortable place. They're trying to spread out. Same thing happens with the air molecules right here. Wonderful. Okay. So before we move on though, global winds and local winds. So wind, again, is the movement of air. Uneven heating of the air in the atmosphere creates air temperature differences. We learned when we were talking about water molecules and their density differences that when we increase the temperature, we are decreasing the density. So as we increase the temperature of our air molecules towards the equator because it's getting more direct sunlight, we are decreasing the density of the air. Okay? Air that is warm expands and therefore is less dense and has lower pressure than colder air. Wind is the result of the air pressure and density differences caused by warm and cool air. Air flows from high pressure areas to low pressure areas, creating wind. Okay? And you're going to watch a video on this and create a Venn diagram, so you will get to know this very well. But we have areas of high pressure and areas of low pressure, and they are distinguishable with some characteristics and weather events that we're going to talk about. But areas of low pressure are categorized by hot air rising. So remember, because things warm up, they're less dense, meaning that they rise in the water and in the air. So that hot air rises. This leads to clouds and precipitations. And due to the Coriolis, winds rotate in a counterclock motion. This low pressure system can cause a cyclone, which is a tornado. So if you get extreme areas of low pressure, you might get a tornado. Areas of high pressure are characterized by cold air sinking again, so the air cools down and it goes, the air cools and it goes down. The wind blowing away, winds blow away in a clockwise motion. This high pressure system is often called an anticyclone because it is not going up like a tornado or a cyclone would, it is going down and out, called an anticyclone. Wind is caused by flowing air, again, from high pressure to low pressure, and the direction is influenced by the Earth's rotation. And we'll learn about the global wind patterns in another day. But what makes some places windier than others? There's two factors. So the pressure differences between high and low pressure and the Coriolis effect. First, pressure differences though. Wind is caused by differences in air pressure. The greater the difference, the greater the wind speed. So if I have a really, really high pressure system and a really, really low pressure system, I'm going to expect really strong winds. By looking at the isobars, the lines that are closer together, they indicate a steeper pressure gradient, meaning that if my isobars are really close, we're going to have high winds, and if they're spread apart, we're going to have low winds. So if we go back to our isobars right here, these are pretty spread out. I mean, think this is the state of Michigan, and we have not a big difference right here as far as going from areas of high pressure around here to low pressure, so I would expect low, gentle winds. In contrast, though, we've got a steeper gradient around this region right here, so there might be quite windy in this region of Canada. Oh, we were actually going to look at that. So where is it windier? Raleigh, North Carolina, or Louisville, Kentucky, based on this graph right here. Here's Raleigh, and here's Louisville. If you look at the isobars on this weather map, you can see that Raleigh, the isobars are really, really spread out. You've got a big gap right here. But if you look at the Louisville, Kentucky, you can see that these isobars are really tightly packed together, meaning that I would expect a lot of wind in this general region right here and less wind right here. So to answer the question, Louisville, Kentucky would be windier. The other thing affecting the wind is the Coriolis effect. Remember, this is what happens, or the phenomenon when things are spinning. The rotation of the Earth deflects the wind in the direction of the spin. In the northern hemisphere, just like with our currents, it's deflected to the right. In the southern hemisphere, it's deflected to the left. The faster you move, the stronger the effect. And there's a video on the Coriolis effect. I might put it on your thing as an additional reference for you today to further understand this lecture. Global winds. Okay, so winds are kind of confusing. They're pretty tricky, but we're going to talk about them, and hopefully this will help. So winds are caused by the uneven heating of the Earth's atmosphere. The equator gets more sunlight. We've talked about that again and again. That means that it is warmer, and the air is warmer right there. Remember, when we said our air warms up, we have a lower pressure. So at the equator, we have, if everything were to stay the way it was, we would have a low pressure right there. Equatorial air expands, rises, and flows towards the pole, because remember, we're trying to keep, we are trying to stop the gradient. So everything in life wants to reach its equilibrium. So that's what it's trying to do, is trying to reach the equilibrium, so it goes towards the poles. As it goes to the poles, it's colder there, so it cools down. Once it gets to the poles, it's denser, and then again, it wants to reach its equilibrium, so it goes back towards the equator, trying to reach that equilibrium. So this is how it would work if the Earth was not spinning like it is right now. So without the Coriolis effect, this is what our winds would look like. They would always flow, well, they would just flow north and south. There would be no east to west. But however, we have the Coriolis effect, which creates these spinnings of winds. So due to the Earth's rotation, instead of having two cells like this, 1, 2, moving in the directions of the poles, we actually have 6. We have 6 because we have a high pressure system around 30 degrees latitude and a low pressure system around 60 degrees latitude right here. We have named these 3 winds in each of the hemispheres. The first one is the trade winds. The second one are the westerlies. And the third one we call the polar easterlies. So the trade winds blow from the east, so they go from east to west. Our westerlies blow from the west. If you're looking at this red arrow right here, we're blowing from the west. And our easterlies blow from the east, the polar easterlies, okay? Now this might necessarily, I hope that you know this, and we're gonna get this down, but it's gonna take us a while for sure. Remember that our high pressure sinks and our low pressure rises, because again, they're trying to reach that equilibrium. Differing air temperatures around the world cause winds that loop across the planet. The sun rays strike the earth more directly near the equator than near the poles, so the air heats up more near the equator than the poles. Because of that, the warm air from the equator rises and towards the poles, while cold air from the poles moves towards the equator to replace it. So because this air is trying to move towards the poles, the cold air replaces it at the bottom. This is what would happen if we didn't have any rotation of the Earth's surface. But because we have the rotation, we have 6 cells instead of 2. The Earth's rotation, combined with these differing air temperatures, causes the movement of air from the equator and the poles to curve in different directions. This is called the Coriolis effect. The Coriolis effect causes winds to curve to either the east or the west, creating predictable wind patterns in different parts of the Earth. So these are predictable, so predictable that we did not hijack, when sailors were coming from Europe and Africa, they would use the trade winds to bring them over, and they would use the westerlies to go back. So they knew these were predictable enough to bring cargo and people over and then take them back. Okay, so in their sailing ships, they use these winds. That's actually why these are called the trade winds. They got their name because traders would bring supplies from here to there, and then they would bring supplies from here to there, but we called those the westerlies because we wouldn't want to name them both trade winds. Okay, and this is the end of your notes today. Let's make sure. Right here. Yep, this is the end. Make sure you turn those in. The last thing that I need you to do today is to please go and complete the following Venn diagram comparing high pressure and low pressure systems. So you're going to watch this video. You're going to do this Venn diagram. Again, you're going to need to go to File, make a copy, and change the share settings to anybody with the link here. And then you're going to use the video to fill in the Venn diagram. So they're guided. Again, you're going to use the video. You can either play right here or play right here, and you're going to fill in this Venn diagram comparing and contrasting high pressure and low pressure systems. For bonus points, an optional assignment, and I'll put 5 points on your last test or the test that you'll take before Thanksgiving. You're going to make a homemade barometer using the steps on this website. Track general air pressure for at least 3 days and email Ms. Backover 1, the results or the lines on your paper with the dates, and 2, a picture of your finished barometer. Here's your wiki how and how to do it. You need, let's see, a balloon, a glass jar, a rubber band, some glue, and a straw. And then you need a piece of paper to track the changes in air pressure, and you'll put a line where the straw meets, where the straw either begins or ends. And then as the air pressure changes, this is going to go up and down. Okay, that's bonus though. All right, if you have any questions, please email me. Have a great day.